countries, they can tackle this in different ways. So we hear a lot about places like China and some other countries deploying drones and all kinds of things to get data on how people are moving. And this is great because obviously it provides like high resolution. You can move the camera at will, and you can also attach additional sensors to it. But in the UK, unfortunately, we don't have the permission to fly drones over crowds and low altitude and things like that. So we have to find a different way of doing it. The government provides some information on like transportation usage, and this is all well and good, but it's kind of like at a macro level, So if we're talking about the number of bus journeys reducing, the number of tube journeys reducing, does this tell us about like how people are gathering? Because they're two separate things. You might have a much fewer quantity of bus trips, but if all the people are packed into one bus and they all get off at the same place, then maybe that's not as effective as you might initially think. So to start this off, we kind of had a look at what's data. So TfL, Transport for London, has 700 plus cameras that they provide on their JamCam feed. I believe there's probably more cameras. There's probably thousands of cameras in total, but they provide about 700 on their website, TfL JamCam. And these are monitoring the streets of London. Their primary use case is traffic congestion and to allow people to, understand if they can get home on time, if the traffic's all jammed or not. And they make this publicly available for people to experiment with. And this is what we've done, really. So we can see these three images here. They're all from November the 5th and different locations around London. So this one here is on the bridge over to the Houses of Parliament. This one, I think that's Marylebone, and this is Earl's Court Road. And so we can see people here. It's higher resolution enough to make the people out clearly, but it's not that high as a resolution to identify people, because we don't really want to have that level of data, because then we have privacy concerns. So we started looking at this data set and said to ourselves, like, what can we do with it, and how can we utilize this? But first of all, we had to kind of take into consideration data quality issues. Because the data set itself is quite noisy. Not every single image is nice and captured crisply, such as these. So every once in a while, TfL is actually using the information for emergencies or some other use case where they don't want the public seeing things. So this could be like a crash, it could be something else. So sometimes, we don't have information at all. In other cases, the cameras have these strange artifacts where the image hasn't been captured or transferred correctly, and this can cause noise in the image. And when we're talking about like computer vision, these kind of noise artifacts can play havoc with the algorithms. So we need to take this into consideration. Under even conditions where the cameras are working fine, we have artifacts that come out from fog and lighting effects. Because these cameras are operating 24 hours a day, we get the lighting changes, we get the weather. I've not got one here, but we also have images where the entire camera lens is covered in rain. And so that creates data quality issues as well. So this is it's a real world data set, something probably quite a bit different from highly curated data sets that are publicly available. You think like ResNet and things like that, Cocoa, they come with really nice images, and these things aren't too much of a concern, but this is a real world data set. Data volume, just to kind of go over some of the data volumes that we have. So as I said, we have 700 cameras, give or take. For each one of those, there's a 90-day history stored on the JamCam website or in the servers. And these are being captured at roughly 5-minute intervals. So therefore, we have our data comprising of this. So we have just over 18 million archived images over the entire network. This comes down to 201,000 daily images the data volume itself isn't very high, really. The images are small, so data volume isn't really a concern. It's more the variety, because we've got 700 different locations, which bring with it 700 different scenes within the camera, and therefore 700 different ways in which the people kind of look, because you've got different perspectives, different zoom ratios, and various other things that create quite a lot of variation within the data set. So that's really the main dimension that makes the data challenging, the variation within it. We started scraping the 90-day history starting from the 1st of February, so that takes us back to roughly the 1st of November last year, and we're scraping this on a daily basis, so we should hopefully build up a nice history of data as time goes on. So what idea is it we're trying to test, and how do we use GCP to help expedite actually testing this idea? So first of all, as I said before, we want to obtain this 90-day image archive history, and then we want to ingest daily, develop a model.
Sorry to interrupt, Sam. My apologies. Just wanted to quickly check. I have read a comment to say that some of your folks are not able to see the screen. I just wanted to check, like, if you're able to see the screen.
Yes, it works now. Thank you.
Thanks. Sorry, Sam, please continue. Thanks.
Okay. Yeah. So yeah, please shout up if anything goes wrong. Yeah. So ingest the data daily as well. Develop an object detection model so we can pick out the people. Later, we might also look at traffic as well, so counting how many buses go down the street, maybe count motorcycles or bicycles, and differentiate people from those kinds of objects. But for now, we're just kind of counting people. And run this over the entire data set, so the inference needs to be computed over all of the 90-day archive, so we can build up some statistics about how many people there are in each scene. Run daily inference, and then generate some plots to understand what it is that we see. So I guess in the spirit of the agile way of working, like make it work, make it right, and make it fast. This is at the make it work phase. Being a data scientist, I don't really know as much depth as a lot of people who work in the platform space do about servers and Kubernetes clusters and all that kind of stuff. So my perspective is really making this work from a data scientist perspective. How can GCP enable me to work fast, move quickly, and get down to this last bit here, which is really what I want to do. So first of all, getting the data. How did I go about this? So I built a Docker image that runs beautiful soup, the Python library. You might be familiar with this, which allows me to provide a URL and then get all the content and interrogate that to get the image URL. And then I can just download that URL into GCS, and that's my image saved. Because of the volume of data, though, if I wanted to do this locally on my machine, it would take quite a while. And I don't really want to do that on a daily basis. It's a thing that I would have to do each and every day. And exciting as it is for the first couple of days, I'm pretty sure I get bored after the third day of doing it manually. So I wanted to run those containers in the cloud. So to do that, I'm using an ARM machine, the Apple M1 Mac. So initially, when I pushed my containers into the cloud, they were built for that ARM64 architecture and didn't work. So I had to find this docker buildx command. Then that worked, but then I realized that gcloud and its platform container system thing allows us to submit this command down here, and it builds it all in the cloud for the appropriate architecture. So that was a nice way to kind of expedite building the containers. But once they're in the cloud, then I could easily run them with Cloud Run. And like I said before, I didn't want to have to manage clusters or servers. I just wanted the container to run. So using Cloud Run was a really nice way to do that. And after a little bit of experimentation, I got my configuration correct so that I could download or interrogate and download the images for one particular date, of which is about 200 to 300 images, and that was taken just over a few minutes. So that container was up and down, and it was quite low cost. So to kind of schedule this at bulk, I used the PubSub platform service to trigger the multiple Cloud Run instances at a single time, and therefore I could leverage these operations in parallel. I could leverage the massive write capacity that GCS has. So scraping in all 900 partitions of data for the initial ingestion, so 90 days in 10 locations, that didn't take very long at all because of the way I was doing it here. And so that was a really nice feature, I thought, of Google Cloud, because if I'd have done this on my local machine, it would have taken most of the day, if not a couple of days, given internet speeds and things like that. So that was a really powerful way to do it. And then daily ongoing ingestion, I'm using Cloud Scheduler and a Cloud Function to trigger the ingestion via PubSub. So I think it's at 10 past midnight every day. This Cloud Function generates the configuration to execute. It publishes those topics to PubSub, and then Cloud Run kicks off and downloads all of the data. And this has been running now for over a week, maybe a couple of weeks, and it's all kind of working really nicely. So this is a really nice way of getting the data, and then we can move on to the next stage of building a model. So the first thing to do when building an object detection model is labeling the data, because if you haven't got any labeled data, you're not going to be able to build a supervised model. So bounding boxes are what we need around the people in the images, and I spent a few days kind of examining the different images and doing the labeling, and then we can go ahead and build a model. So in Google Cloud, most people have probably heard about AutoML and Vision. So the AutoML Vision object detection function is what I was using there. So the process really was just to extract the annotations from this tool here, which is called rect label, transform them into the format that AutoML uses, upload everything, and then kick off the model training process so that we have a model at the end of it. This took a few iterations. Obviously, getting things working quite correctly can be challenging, so I spent a bit of time iterating around a few trained models, just experimenting with some of the hyperparameters, swapping out some of the locations that are used for the labeling, because some locations, when I added labels for those, they kind of skewed the model off. I think it's more likely due to image artifacts within these images. So I had to exclude a few locations, and then add in some additional training data, and it seemed to do quite well after a few iterations of that. So that was quite good. When we come down to batch prediction, though, this is another useful feature. When the model is trained, it's available at an endpoint, but that endpoint is essentially a REST endpoint, and trying to push millions of images through there is going to take quite a lot of time and cost quite a bit of money because of the provisioning of the endpoints. What AutoML allows us to do is have the batch prediction route, so we can provision how many images we want to predict, and then let it manage the infrastructure behind the scenes to do that. So that took a few hours to iterate over the initial data set that I pushed through it. So at this point, this was allowing me to work really quite quickly to keep testing these ideas to say, how accurate can the model be? How does it scale to different locations? And what information can I get from it? So using the model, so now we're moving on to kind of what do we do every day. So as I said before, labels are uploaded and we have the model built. And then the daily schedule consists of post, the data being ingested, we then wait a little while until that process is finished, and then kick off another schedule, which again generates the configuration, runs Cloud Run to get the new images, predicts with the model, and then saves everything to disk and into database. This is Firestore, and into GCS. And then we have our data ready now for interrogation and analysis. So we can see an image here of the bounding boxes. So this is counting the people on the bridge over to Westminster. You'll probably notice in the background, we can identify some people that the model's missed. This is something I'm going to be working on because I think the model can probably do better. It just needs more training data and perhaps some tweaks and a custom model as opposed to the AutoML model. But it's something I'm working on. But other than kind of people in the background, it does do quite a good job of picking up all the people in the foreground and allowing us to count those. So I guess the story here is we could test this idea, in less than a week and get some pretty good results. So then the next thing to do then is to look what does it actually tell us. So these plots here, or this plot, is for the aggregated count across the entire network that we analyzed at the 90% confidence interval. So we can kind of see, over the Christmas period and the New Year period, there was a bit of a spike in traffic prior, and then it reduced. But given the uncertainty across different locations, it's probably worth further analysis of those different locations. And then if we drop it down to the 40% confidence interval, it tells us essentially the same story, but with just more uncertainty. So if you look at the different shapes here, we see this kind of rise around the 12th of December the 1st, and we see the same peak here. It's just there's more uncertainty because we're at the 40% confidence level as opposed to the 90%. So it kind of tells a consistent story. If we look at some different locations now, what we kind of see here is this bridge over to Westminster. It's been pretty consistent. We see less variance at Earl's Court here, so it's more consistent and less spikes than there was in the period prior to Christmas. So that's good news, I suppose. People are following the rules. We see a trend coming down here and then some consistent behavior, which again kind of echoes that message. This one is fairly consistent the entire way across, or you could argue it's dropping. So we're seeing some, I think, useful information coming out of this, which can be used to maybe guide policy or understand how people are actually moving. If we look at some other kind of plots, so this tells us some different information. So this top box plot here is showing us the predicted count at the 40% confidence interval over a day of the week. So I should perhaps expect Saturday and Sunday are quieter than the week. The reason being this is a working area, so people typically don't frequent there at the weekend so much. And then this box plot here shows us the time of day or the hour. And again, a place of work, there's more traffic in the morning when people are arriving. And then I guess you could say that people are leaving in a staggered pattern in the afternoon, starting at 3 and then maybe finishing at 6 or 7. So this is, again, it's showing the movement of people. If we look at this one, this is kind of an interesting plot because it kind of reinforces the message, really. So we've got a grouped box plot by day of the week and hour of the day, but the hours being capped between 6 in the morning and 9 at night. And we can see that at the weekend, so like at 2 o'clock, 3 o'clock, at the weekend, we do actually see Saturday as the highest traffic time at the weekend here. Whereas at the weekend, early in the morning, we're seeing hardly any people, which you kind of expect. So this is, I think it's useful information. And since we're able to get this plot out within a week or so using GCP, I think it's quite a good message for using the machine learning services there, really. This is another location. This is a more residential area. And I suppose what we're seeing here is a reflection of that. So the traffic's more or less consistent across the week. You're getting a spike around lunchtime or just after lunch, mid-afternoon, which you might expect. And then this one down here is kind of just showing a similar kind of story. There's no, there's no major shift in behavior over the days, as opposed to like a working area primarily. So that was kind of what I wanted to present. Then what's next for this? I want to expand the scope to ingest more cameras so we can cover a larger network. Publish some charts to Twitter. I think it might be interesting to do that to see what people think. Build a mobile app maybe and make an Alexa skill. The reason for that is, you might want to know the time of day to leave the house with less traffic on the streets. And you could do that by interrogating the data set because we have this information to hand. So that's what's next for this, really. So if you have any questions, I'd love to answer them or any comments.
Hi, Sam. Sam, thanks ever so much for that. Hi, everyone. This is Tim Jones. I'm sorry, I should have been welcoming you for the meetup, but I had technical issues. So thanks to Siva for taking over. Sam, we've got a couple of questions. One from Conrad. He said, how did you exclude problematic images?
Okay, so the first step was to classify images. So as opposed to just pushing through all the images, we can classify those images that are good and those that are bad with an additional image detection technique. So object detection works on bounding boxes, but we can use image classification to classify those that are just no good, essentially. Other areas I'm looking at is trying to detect artifacts that are a little bit more kind of difficult to work with. So when you have lots of fog and reflections, I'm currently working on a technique to try and exclude those as well. But for the ones that cause most of the problems, we can use classification on it.
Cool, great. And one from Marcin, he said, did you consider outsourcing data labeling to an external company?
I did, yes. There's various techniques to do that. And that's something to look at as it scales, essentially. At the moment, because it's an idea and I'm just trying to work on developing the proof of the idea, I didn't think it was necessary, but it's something that we could do, yeah.
Cool, cool. And Chris has asked, do you know the approximate cost for running it per month? I mean, obviously this would depend on, Google pricing and whether you run it in Google or elsewhere, but any idea of rough order of magnitude?
Yeah, rough order of magnitude. So the get data phase operating daily, those costs are less than a couple of pounds a day. Data storage is maybe a couple of pounds a month because it's stored in GCS. The most expensive part of the whole process is the model. So depending on what model type or what hosting type you use for the models, it can start to get expensive. Obviously, if you're gonna do something crazy and have like a GPU instance spinning up there 24/7, then that's gonna cost you a couple hundred or maybe knocking towards £1,000 a month. If you use a low spec instance, because image and model inference doesn't need a lot of compute power to do the inference part, you can get that down to £100–150 a month quite easily. If you're running some different clouds, the costs also varies quite a lot. So AutoML as a platform service is cost effective actually. If you were to run this in something like Recognition, then that could get very expensive. I've not looked at the cost in Azure, but for AutoML and hosting, it's quite cost effective.
Cool, cool. Interesting. It throws up some interesting things that clever developers could do around spinning up something, taking these feeds and then producing an app on a mobile phone that says, is this tube station busy, is that one busy, and not relying on I don't know, the BBC News to say it, but looking at it and actually seeing the feed and then working out the best time to go to work and stuff like that, and then get someone to sponsor it, which will cover all your costs and maybe make a profit.
Yeah, absolutely. I mean, it's kind of like citizen science. This data's out there. I don't think there's really any privacy concerns around tracking individuals, because you've seen the images. I think if you were to track, or if you were able to track an individual, you'd have to be doing something pretty darn special, or the person would have to wear the same thing every single day and make it bright red or something.
Yeah.
So I think privacy is not too much of a concern, but I think there's lots that could be done with it, and especially as you look at like data fusion between different data sources that are provided.
Cool. I have heard of a use case where I think Westfield have used something like this for tracking data, not to take in individual people, but overall mass. And they would track people walking through Westfield shopping centre, and they would use it then to sell premium advertising spots to sponsors and other people within Westfield. So there's a business case in there for something. But no, it's really good. Thanks, Sam. Really appreciate it.